2 YouTubers die on Nürburgring. Great.
Hey everyone, I'm joined by Roman, aka Der8auer, and we're at LTX 2019. So first of all, I'll go ahead and thank Linus for bringing us out here and making this possible. And Roman, we want to talk about thermal paste.
Correct.
Today. Before that, this video is brought to you by EVGA's new audio sound card, engineered by AudioNote. EVGA's CEO knows high-quality audio and has begun bringing sound cards back. The new audio sound card is capable of delivering hair-raising audio superior to onboard sound. The card includes a line in, headphone line out, and mic in, and a Sony Philips digital interface. New audio also leverages EVGA's PCB design experience, has upgradable op amps, and uses AKM premium components for its DAC and ADC. Learn more at the link in the description below. There's actually a lot of interesting aspects to thermal paste. I think on the surface, it's like, well, it's a thermal interface.
Yeah.
But there's actually some really interesting stuff. So topics like curing, how the paste ages.
Yes.
You were talking about a pop-out effect, so we'll go over that a bit. And optimal operating temperatures.
Yes.
And should we note, I guess, thermal grizzly affiliation?
Yeah, I mean that's one reason why I'm not doing any like thermal paste testing anymore. I used to do that quite often, let's say 4 or 5 years ago. That's when I got into thermal grizzly because I did testing for thermal grizzly before I started to own part of the company.
Right.
And now that I'm owning part of the company, obviously I cannot do that anymore. It would be kind of wrong.
Right.
That's why I'm not doing any like thermal interface testing anymore.
The good news is for this video though, it does mean you have a lot of actual first-hand knowledge with making thermal paste.
Exactly. Yeah.
So you got the behind-the-scenes information on getting it made.
Yeah.
So where do we want to start? I mean, with making a thermal compound, I guess you probably pick like what you want it to do, maybe a price, something like that. After you get through that and figure out what product you want, what considerations do you have for material properties?
When we started developing products, I mean, I also started kind of at zero. I didn't really know what everything was about and did some basic research like what is a thermal compound made of? And then we started basically mixing stuff ourselves. So I have a glove box at home, it's called. It's a box where I can have an environment inside with 0 oxygen.
Oh, okay.
Because some of the powders that are used inside the thermal compound can be very dangerous when they're exposed to oxygen. For example, a lot of compounds are using aluminium powder.
Okay.
And aluminium powder is really reactive. If you open the box of aluminium powder just in ambient air, then the water inside the air will like react with the aluminium. Then you will have like gases forming that are explosive.
Okay.
So it's really, really dangerous.
I was gonna ask, yeah.
So we had to get all that, and then we basically started testing. And the key of a thermal compound is you have to have a base material, which is basically like a silicon oil, as a carrier to have it somehow
make it so you can spread it.
Exactly.
Okay.
Yeah, and have the particles inside that are transferring the heat. And for that, you would use something that's like copper, aluminium, metal. That's very good at heat transfer. But also you have to be able to grind it really, really small. Like the particles have to be extremely small to go into the very fine gaps.
And a lot of these, do these make a paste conductive, I guess, if you're talking about using metals like copper?
Partially. Okay. The thing is, for example, you could use aluminium powder, and using it inside the compound itself will make it non-conductive because you have all those oil particles surrounding the aluminium particles, kind of insulating them. So therefore, using it in the compound will make it non-conductive. It's the same with the silver pastes. It will make it non-conductive, but you have other effects. For example, it will be capacitive.
Okay.
So that's something that really doesn't matter on a GPU or CPU, but there are some electronic applications. If you put it on like a PCB and stuff, it will act like a capacitor, for example.
Okay.
So there's a lot of stuff you have to consider. Yeah.
Is ceramic, is that another material that's used?
Ceramic is just a name. Ceramic is basically also aluminium oxide.
I see. Okay.
And aluminium oxide is also one of the most used particles inside thermal compounds. The most commonly used stuff is zinc oxide. Aluminium oxide, aluminium particles, that's the stuff that's most commonly used.
So for a cheaper paste versus a more expensive paste, where does the line start getting drawn with quality? I mean, what is it moving from like a zinc to a copper or something?
You have to get also the right mixture. You cannot just say, okay, I will use 100% aluminium because it's the most expensive. It will lead to the highest thermal conductivity. There's more to consider. You have to use different particle sizes, different particle shapes as well.
And to achieve the sizes and shapes, do they grind down the base metal in like a bar form or something?
I actually cannot really tell you how that's done. And also, we also source those materials from different vendors. Like there are shops where you can say, I want to have 1 ton of aluminium powder with 20 nanometer size and this shape. And you can buy those on specific stores. Yeah. And that's what we do as well. And then you get your different materials in different sizes, different shapes. Then you have to test what kind of mixture will give you the best results. That's a lot of trial and error.
Well, testing thermal paste is, as you know from even before you did thermal grizzly work, is probably one of the hardest thermal items. You can test CPU coolers, you can test fans reasonably well with an actual system, but it's still not perfect.
Yeah.
But once you get all the way down to the paste level, it's impossible to use just a computer.
Exactly. That's why we developed our own thermal testing stands. The easiest is still using 2 pieces of metal, like 2 copper plates. You have one that's heating, one that's cooling down, and you have to have very accurate temperature sensors, like high precision temperature sensors, and then just measuring the delta in between. What you also have to keep in mind always, the pressure is really, really important.
Yeah. So do you have to mount them with the same torque or something?
Yes.
And then do you follow the same screw pattern each time?
Exactly.
Okay.
It's very similar to mounting like the top of an engine in a car. You have to have exactly the same pattern of the screws, same torque wrench and everything. Yeah.
So for testing then, is it similar to what you used to do? Because there was that, what was it, overclocking.guide? Is that what you used to write for?
Exactly.
And you did the whole build, right? Like you showed I think you got something CNC'd or something.
Exactly. That's the first test we used, or the first test bench we used for testing thermal paste. And then we have like one that's much more advanced right now.
So now that you've improved that process, how do you feel about your old guide? I mean, with what you know now about paste, when you look back at it, are you like, I could have improved this a lot, or do you feel like it
was actually pretty accurate? Yeah, it's very accurate as long as you follow the same steps. If you mount the cooler always the same way, if you tighten it completely, like the springs are completely tightened, then it's roughly the same pressure. The thing with the pressure is also, it only helps so much. Like let's say you're using a pressure of like 150 Newton to 200 Newton to your CPU, that will help. But increasing it to, let's say, 800 or 900 Newton, it's not going to do much.
Okay.
So as long as you have this base pressure covered, everything else above is not going to do much.
So what, for actual use, let's talk about the pop-out effect?
Pump-out effect.
Pump-out. Thank you.
Yeah.
So what is that?
The pump-out effect.
I clearly don't know.
Yes. That's one of the most crucial, most important things that happens in thermal paste applications. You know, all those Intel CPUs that say 6700K, you open it and the thermal paste looks dry.
Yeah.
It's actually not dry. That stuff in there is supposed to be exactly like that.
Okay.
It's from the first day it looks like that. It's never like it was wet before. It's always dry. The reason for that is, for example, Cryonaut. It's a very wet thermal compound. It's very flexible. And if you apply it between, let's say, a GPU and a copper cooler, and you give it, let's say, 2000 thermal cycles, you have a different expansion and shrinking of the cooler and the die. And during those processes, the thermal paste will work its way out. At the end, there's almost no thermal paste left between the die and the cooler.
Okay.
And that's the pump out effect. And that happens especially on very wet thermal compounds, which usually have a much higher performance. For example, that's why we typically recommend, if you're using Cryonaut on a GPU, replace it like once per year. Then you're safe.
So it's an actual recommendation, not a we'll sell more paste if you replace it once a year.
No, really. You will see a temperature gain, and that happens for, I would say, 95% of the pastes on the market. Especially all the high-end pastes, they all have this issue.
Is it typically the more liquidy pastes?
Yeah.
Okay.
Yeah. For example, Hydronaut will have much less of this effect.
Hydronaut's pretty viscous, right? It's a little harder to spread.
Yeah, but Hydronaut is also not silicon-based,
Okay.
and Cryonaut is silicon-based, which is a lot better for like very low temperature applications. That's why we picked like silicon for Cryonaut, but non-silicon for Hydronaut.
Okay.
And this pump-out effect, that's why a lot of people they're underestimating what Intel, for example, has to choose for a thermal compound. They have to pick a thermal paste that's the same performance on the first day and after 10 years. And that's the pump-out effect, yeah. That's also a big problem on notebooks, for example. We have a lot of, like, let's say, HP or Dell, Asus. They all reached out to us for improving thermals. And pump-out effect is typically the biggest problem, yeah.
So what about curing? Is there's a curing time, I guess, or an amount of thermal cycles at which the paste begins to harden for some of these compounds? So
most of this, what people are considering curing is the pump-out effect.
Okay.
So thermal paste typically doesn't go bad. It's not like that. There are some compounds that are using very cheap oils as a base material, and they can kind of dry out.
Okay.
But besides that, it's 95% or 99%. It's the pump-out effect that's causing aging in
what
thermal
people
paste.
perceive to be curing.
Yeah,
I guess.
if they see that the temperature goes bad, it's mostly because it's pump-out effect.
Okay.
Yeah.
What any other considerations or common misconceptions?
So one thing I really like is the air bubble effect people are saying. So you're spreading your thermal paste across the whole surface, and then you're putting your cooler on, and they're saying, but if you put your cooler on, there's air bubbles between the CPU and the cooler, and it will lead to bad performance.
I've never seen that comment.
No, you have never seen
No.
that?
It must just be you. It's just the German.
Can you please leave a comment down below that you've heard that before?
Let's not do that.
That's yeah. So the air bubble comment, that's complete bullshit.
Okay.
Like completely. If you imagine how much pressure the cooler is putting onto your CPU, like there's just no air between your CPU and your cooler.
Well, that's the whole point of thermal paste, is to fill the small gaps in the middle.
Yeah. So it doesn't matter.
It wouldn't work if that were true.
It doesn't matter if you spread it or not. No air bubbles.
Okay.
That's complete bullshit. Also, some thermal paste manufacturers are stating that it needs time to have the perfect performance.
I've heard that, actually, yeah.
No.
Okay.
No.
So I had a thermal paste manufacturer say that we should let their paste sit under a thermal load for 2 hours before it's like ready, I guess.
One reason they could say that is your layer could be a little bit thicker, and when the temperature increases, it becomes more fluid.
Right.
And then some parts of the thermal paste will be squeezed out due to the pressure of the cooler. And because of that, it can increase in performance. But that's just because you're thinnering the layer, right? Yeah. That's the only reason it could be.
So if you apply it the same way every time, and it's a thin enough layer, then it doesn't really matter.
No.
Okay. What about other common misconceptions on paste? What about too much versus, should we talk about too much?
Too much, I loved your video on too much.
Yeah, because I used the whole tube of Cryonaut on it.
Yeah.
I had to buy another tube after that. Of course you loved the video.
Thanks.
That video made you $13.
Good point.
Yeah, so too much. We did talk about that one, but in general, I guess as long as you're applying pressure onto the surface, it'll squish out.
Yes.
So is that pretty much what you found as well?
Yeah, any amount is fine. I mean, if you use more, it's great for me.
The only downside to using more is if you're using an electrically conductive paste, I guess, and it squeezes out to the point that it touches something that it can short.
Yeah, of course. I mean, if you're using conductor for example, really use as less as possible. And if your performance is bad, that's fine. You just remove the cooler and add a little bit more instead of having too much and squeeze it out somewhere.
Yeah, definitely.
Yeah, absolutely.
Any other?
Yeah, liquid metals are very, very interesting, actually.
Okay.
Liquid metals, they're mostly the same because they're all based on gallium, indium, and tin, most of them.
Is that, by the way, is that mixture called Gallinstan, or is that something else?
Gallinstan is a specific name for one specific mixture that has, I think, the lowest melting point. So it's liquid until minus 19 degrees, I think. But it's just a name for this very specific mixture. But that mixture doesn't really have the best thermal conductivity. For liquid metals, it's a little bit different than compounds because it's an alloy. And the rule for an alloy is that the more metals you add, the worse the conductivity becomes.
Okay.
So let's say
the more types of metals you add?
Yeah, and the more types and also the percentage.
Okay.
For example, you would start with 100% gallium, would have good conductivity. If you add 5% indium, even though the conductivity of indium is higher than gallium, it will lower the total.
Okay.
So that's what happens with alloys. So you can just play around with alloys and add different metals and see how it helps, for example, on spreading and curing. And for example, the gallium will react with any metal, actually. It's like very corrosive.
Right.
And you can add some metals to prevent that a little bit. So you can play around with that. But the more you add, the worse the thermal conductivity becomes.
Right.
Funny aspect also about liquid metal is that the higher the temperature is, the better the thermal conductivity becomes.
We've had a lot of people ask, why don't you use liquid metal when we're doing LN2?
Yeah,
that's why.
That's the exact opposite effect.
Yeah.
So on very low temperature, the thermal conductivity of a liquid metal is really bad. You can just look up let's say alloy and temperature conductivity over, or the conductivity over temperature.
Right.
And you see like minus 100 conductivity is much worse than any conventional compound.
Yeah. Should we do this? One other topic I've discussed with do you know who VSG is?
VSG?
Yeah. He writes for Tech Power Up now.
Yeah.
But he's a postdoctorate thermodynamics researcher.
Mm-hmm.
And I was talking with him about thermal conductivity and how a lot of the thermal conductivity ratings are, one, not measured the same way, so you can't necessarily compare between people.
That's correct.
And two, often not measured correctly.
Correct.
So is this a better topic for a separate video to talk about, or is it short enough that you want to address it here?
I can quickly address it. It's basically you have there are certain industry standards how you measure thermal conductivity, but there is no set standard for thermal compounds. There are different ways to measure, and the different ways will always lead to different results.
Right.
One big problem is also that there is no given temperature. I mean, you would always assume to use a temperature of 20 degrees Celsius, which is something I don't agree with. For thermal compounds, it doesn't make sense because the operating temperature is always higher.
Yeah.
That's why we use, at least for thermal grizzly side, we always use much higher temperature than 20. I cannot tell you what we're using.
That's fine. But I think the question, though, is, so if you use a higher number for your assumed temperature, operating temperature, does that make, I don't know what the formula is, so does that make your thermal conductivity value lower or higher?
Higher.
Okay. But it's also more realistic to the
use
case.
In my opinion, it's more realistic to test, for example, at 50 or 60 degrees Celsius than at
20 degrees is like an air-conditioned room ambient temperature.
Yeah, you would never have that.
Yeah.
So that doesn't really make sense.
Right. So are there any other variables in there that kind of get changed between manufacturers that you can talk about?
Not really.
Okay. But I guess assumed operating temperature is the big one.
Yeah, operating temperature and also the way you measure. There are different, like ASTM, it's called, and you can look it up. But,
okay. Any final notes you want to do? Thermalgrizzly.com, I guess, if you want to plug that.
I can tell you that we're working on a new version of Cryonaut and a new version of Conductonaut, which will be out soon.
Okay.
Yeah.
TBD? No date yet?
The Cryonaut is actually ready, and the liquid metal is not ready yet. So liquid metal maybe in 2 or 3 months. Cryonaut like 1 month, I would assume.
Okay. So probably 4 to 6 months and then 2 months. Would be the realistic timeline.
5 years until Gamers Nexus gets it.
Yeah, very likely. All right, so that's your video on everything you want to know about thermal paste. Someday we need to do like a thermal paste factory tour or something.
I think we can do that.
My assumption is that it's just a giant vat of Elmer's glue, like they use in a kindergarten.
Yeah.
And then you just throw some random stuff in it and make it gray.
Yeah,
that's how I think it's made.
It's
pretty
actually
accurate.
it's very similar to making paint, actually.
Okay, so not accurate at all. Well, thank you for watching. You can check out Roman or Der8auer. We'll link him below. He's got his own YouTube channel, and also Thermal Grizzly for their thermal paste products. Thank you for joining me.
Thanks, man.
We'll see you all next time.
See you.
We can accommodate that. That'll be good content.
Yeah.
I thought we were doing that later in the hotel.
Sure.
Why are you denying it now? That really
We're
hurts
on camera.
That really hurts my feelings.